Here are solutions to test number 2 for ECE 376 embedded systems. This test looks at C programming on a PIC processor, as well as some statistics. The first problem is, here's a program that turns your PIC into a taillight controller. What happens, I have 3 buttons. If I hit RB0, the taillights turn off. If I hit RB1, the left light blinks on and off. That's a left turn. Hit RB2, the right light blinks on and off. That's a right turn. So write the corresponding C code. And actually on this one, you don't really care about the problem. I can just go straight from the flowchart. Each block of the flowchart should correspond to a section of code. So the first one is make port B input, port C output. And C, that's the TRIS registers. TRIS controls input or output. 1 means input, 0 means output. So this makes all of port B input, all of port C output. And you do need ADCON1 equals 0F. That makes everybody binary. The default on a PIC processor is analog. If you want to do something other than default, you need to define it. The second block is I want to initialize the values. Here's my operating mode. This is going to be 0, 1, and 2. I'm initially not turning, and the lights are off. Here's my infinite loop, a while loop. Now I'm going to check. If I hit button 0, I go into mode 0. If I hit button 1, I'll go into mode 1. Hit button 2, go into mode 2. If all that fails, the mode is whatever it used to be. I can now check. What is my operating mode? If I'm in mode 0, turn off the lights. If I'm in mode 1, toggle port C, and one way to toggle it is use the not command. So port C is not port C, 0 goes to 1, 1 goes to 0. And if I'm in 2, I toggle port D for a right turn. Then wait 250 milliseconds. This is a wait routine that we've written before. It waits roughly 250 milliseconds. It just basically goes into a for loop and wastes time until you get to 250 milliseconds. So here's the C code that corresponds to that flowchart. This will be turning your PIC into a turn signal. Problem 2 looks at implementing the following curve in a subroutine. So I pass X, I return Y. And kind of background, this might be like for wind speed or a wind turbine. As the wind speed varies, the amount of energy I output varies. Come up with a curve fit, so I pass X and returns Y. One way to do that are 3 piecewise linear functions. If X is less than 2, I return 0. Otherwise, if X is not less than 2, but is less than 6, I'm this part of the curve. If you do a linear curve fit, this is Y equals 1.25 times X, there's the slope, minus 2.5. I can get that. The slope is change in Y over change in X. 5 over 4 is 1.25. If I plug in 2, I should get 0. That's this line of code. Else, if X is bigger than 6 and less than 11, I'm on this part of the curve. This one has a slope of 4, and the offset, if I plug in 6, I should get 5. And finally, if all that fails, it's a constant 25. Once I find Y, I'll return it, and there's my subroutine. So now if I pass a number like 8.8, it should return right around 16. Problem 3. If I have a thermistor and a voltage divider, I can measure the voltage with the PIC. So if the temperature is, pick your favorite day, like your birth date, is 14 degrees Celsius, I can plug in 14 and find the resistance. Winds up being 37 ohms. I've got a voltage divider. The voltage is R over R plus 3300 times 5 volts. Gives me 2.65 volts. The A to D reading, full scale is 5 volts, full scale is 1023. Is this percentage of full scale? The A to D reading is 542.6. So here I'll convert to an integer, either 542 or 543. Depends how the hardware is built. Problem 4. Problem 4 looks at a t-test. When you take random processes, there's the thing called a Monte Carlo simulation. If I want to find out what's the odds of being dealt 2-pair in poker, what I can do is write a program that deals out 5-card poker hands and counts. How many times did I get 2-pair? That's called a Monte Carlo simulation. If I did that, run that program 3 times, I get 3 answers. Suppose the answers are 4692, 4773, 4646. That data has a mean, standard deviation. Based upon that data, I can tell you 2 things. One is, next time I play it, how many times will I get a 2-pair? And to do that, I need to specify the probability. So this is a normal distribution. It's got a mean, standard deviation. What I want is this area to be 95%, which means I want each tail to be 2.5%. To find out how far away from the mean I have to go to get 2.5% tails, I use a t-table. I have a sample size of 3, meaning 2 degrees of freedom. I want each tail to be 2.5%. So there's my t-score. So when I go left and right, 4.3 standard deviations, and that gives me these numbers. So the next time I deal out 100,000 hands of poker, the number of times I get a 2-pair should be somewhere between 4426 and 4979, with a probability of 0.95. Second question is, there is a probability of getting 2-pair. I can actually calculate that. With Monte Carlo, I can estimate the range with that probability. This is a population question. As I deal more and more hands, I know more and more about what that number is. With a sample size of 3, I take the standard deviation, divide by the square root of sample size. And as the sample size goes to infinity, this goes to 0, so I know what the actual mean is. If I go left and right, 4.3 standard deviations, which again is 5% tails, or each tail is 2.5%. That gives me 4542 and 4862. So the actual number of hands, or as the number of hands I deal goes to infinity, the percentage of them that are 2-pair is going to be somewhere in this range. Divide by 100,000 and I get 4.54%, 4.86%. With this data, I don't really know what the actual probability is of getting 2-pair in poker, but I can estimate it using a t-distribution. And as a sidelight, if you go to Wikipedia, poker's been analyzed to death. The actual odds of getting a 2-pair is 4.754%, which, not surprisingly, is in this interval. So that's the t-test. The last problem is a chi-square test. In this problem, it looks at, suppose you're in a class with 10 people. All 10 of you raise your hand at the same time, and someone else is selected. How many times does this have to happen until you notice, or you can be sure, that people are not being called on at random with a 95% certainty? That's actually a chi-square test. If I have 2 bins, I'm selected, I'm not selected. If it's a uniform distribution, there's a 10% chance I'll be called on. 90% chance I'm not called on. If I raise my hand n times, the expected frequency of me being called on is 0.1 times n. Not called on, 0.9 times n. If I'm never called on, the actual frequency is 0, selected, and not selected. With that, I can calculate the chi-squared score. Take the difference squared, divide by expected value, gives you 0.1n. Difference squared, divide by expected value, 0.11n. Add them all together. That's my chi-squared score. Going down to a chi-squared table, I have 1 degree of freedom, 2 bins. I want to be 95% certain. If the chi-squared score is 3.84 or more, I can be 95% certain that this is not this is not a uniform distribution, that people are called on, the way people are called on is not random. So if I set this equal to 3.84, I can calculate n. Meaning, if I raise my hand and I'm not called on 34 times in a row, maybe round up 35 times in a row, I can be 95% certain that something's up. This is not random. Which also kind of says that if I'm not called on 30 times in a row, that could still just be random. That's a chi-squared test. So that is test number 2 for ECE 376.